It's time to develop our classification model, image classification model in Python environment using convolutional neural network. This image classification, we want to use one of the PyTorch data sets that is called Torch Vision dataset. You can just Google Torch Vision and this website will pop up. If you cannot find it, I just put the link in the resource button. You can just click on it and this will pop up for you. And these are the data sets of PyTorch, or let's say Torch Vision, provided by PyTorch. And there are lots of data sets for image classification purpose here, like for example, food, flowers, I don't know, lots of data sets. The ones that we selected for this tutorial is the CFAR 10 dataset. So if you're curious about other datasets, you can just click on them. If you click on this part, it will bring up the section of the PyTorch itself for you. For example, what are the different parameters that you need to give to this dataset when you want to read it, and so on. And if you click on the second part, second column, for example, CFAR 10 is the one that we selected. If you just click on this, it will open up the source website that actually created this data set, and PyTorch Vision is actually using this data set. So this is the website for the CFAR 10 dataset that we want to use. There are lots of good information here, like CFAR 10 dataset consists of 60,000 of image. The dimension is 32 by 32 color images. And we have 10 classes, as you can see here. The classes are airplane, automobile, the bird, cats, deer, dog, frog, horse, sheep, and truck. So we have 10 classes, 10 different classes, and with 6,000 images per class. So for each of, for example, we have 6,000 airplane, we have 6,000 car, we have 6,000 bird image. And overall, we have 60,000 color images. And there are 50,000 training images and 10,000 test images. So we can separate the data set that is provided to 50,000 for training our data set, our model, and 10,000 for testing our model. There are lots of other good information here. If you are curious about it, you can go through that all, but what we wanted to understand was actually some useful information about the size of the data set and the number of classes and these things. But feel free to go through the website to find out more about this great data set. So let's go back to the Python environment. Libraries that we want to use, like always, we import Torch first. Then we import Torch Vision because we want to use the data set. If you remember, it was from Torch Vision section of PyTorch. Torch Vision. And we also want to import, for creating our neural network, import torch.nn as nn. We import Optim, like before. Import torch.optim for optimization parts as Optim. Oops, I have a typo here. So Optim. And we also want to import Torch Vision. From Torch Vision package, we want to import the method transform as transform itself. All right, so we can easily use the transform method here. And also for the visualization, we need matplotlib. So let's use matplotlib .pyplot as PLT. I think these are all the libraries that we need. During the coding, if we need other library, we can simply import it. But for now, these are the libraries that we need to start our coding. So let's run this. It takes for sure a couple of seconds because it's the first time I'm using this notebook, and you can simply create another code cell. So after, yeah, I guess all of the libraries are now imported. It actually started importing. Oops, we have an error. So module name, Torch Vision transform. All right, so we have a typo here. We need to put S at the end of here, and here let's put it. Yeah, now it's done. So we have imported our libraries. I forgot to put this S, just be careful about this. And now we want to use our Torch Vision dataset. We talked about the CFAR 10 dataset, and we looked at the datasets, looked at the number of classes that we have for this dataset. And the other thing that's before reading the data, as I mentioned, if you go back to the CFAR, the Torch Vision website that we opened in the beginning, this one, the dataset part of the PyTorch website. So here in the left-hand side, as I mentioned, if you click on CFAR, for example, you can see all the parameters that you need to define. So what we need to define for CFAR is first defining a root. So root is a directory which the downloaded image will be saved. So we need to define a directory in our computer. Then the downloaded data, if you set the download to true, this is the download parameter. And in this course, we always put this as true because we are using Colab. We want to download it and save it in the directory to have it when we are coding. So this is the root that we need to define after setting the download as true. And this train parameter is actually one good thing about the Torch Vision datasets is you can directly separate it to train and test sets in the beginning. So there's no need for train test splits during the data preparation. So it actually separates the training set from the test set in the beginning when you are reading the data. And the other parameter is a transform parameter, and transform is when we want to transform our input data. So we will use that when we want to read the data. And let's actually use these parameters and read CFAR dataset. Let's go back to the Python, and I just put a name for it. Let's call it train, for example, because this is a training set. Then I'm using the Torch Vision library that I imported. Torch Vision, yeah. And I go to datasets, and then again I call CFAR dataset. So you can see all the datasets of the Torch Vision. You can see them here. We went through some of them. The one that we want to select is a CFAR 10. So let's click on that. And then inside of the parentheses, if you remember, the first thing that we need to define is the root. So the root is where we want to save our downloaded data. So let's, for example, call it like this, the roots. Let's put it inside of the quotation, then dot slash, let's call it data, for example, okay? And then the next parameter that you need to define is, what is this? Is it a training set or test set? So if I say train equal to true, it means that this is my training set. If I set this as false, it means that this is my test set. So that's defining the training set. Again, as I said, we always set download equal to true, right? And the next thing that we need to define is transform. So for the transform, transform is equal to, because we want to change the input data, the images to tensor, we simply here can mention the transformation that we want is actually transforming the images to tensors. So we used transform is equal to transforms that we imported here. If you remember, Torch Vision, the transform as transforms, dot to tensor, this one, to tensor, and empty parentheses. That's it. So let's review what we have done. We have actually created, put a name for our variable, our dataset train, and we call the datasets of the Torch Vision library. We call the CFAR 10 dataset that we went through it with together. We define the roots as the first parameter, where our data is saved. We define we set the train equal to true. It means that this is our training set. Download equal to true. We want to save the data. And also we put transforms dot to tensor because we want to transform our data set from image to tensor so we can feed it to our neural network. That's it. We have done it. We have actually created our train set. I can simply do the exact same thing for the test set, but before that, let's check the training set. So if I put train and run this, it takes a couple of seconds in order to download it. So it start downloading the data set. You can see here 100%, then start extracting the data for you. And then because I asked what is train, you can print it out. It is mentioning the information of this data set. So data set CFAR 10, number of data points is 50,000. If you remember, the data sets of CFAR was 60,000, 50,000 for training set, 10,000 for testing part. So the number of this train set is actually 50,000 of data points, and the root location that you save, the split as train and standard transform. And we transformed it to tensor. If you want to check the tensor itself, for example, one of the tensors, we can simply say, for example, train 0. This will give you the first element of the training data, the first image tensor actually. So if I run this, it is something like this. So we are actually changing the image, the first image, for example, to a tensor like this. So this shows a tuple here. This first tuple is actually the 32 by 32 image that is changed to that we actually gave value to that image. And this next parameter here in our tensor is actually the number of the class number. For example, 6 is related to, if we go to again to the CFAR 10 data set here, you can see that airplane is 0, car is 2, bird is 3, cat is 4, deer is 5, dog is 6. So here it was 6, right? So it means that this training set, the first element of the training set is actually related to dog category. So that was it. This is what our tensors look like, and we are giving these tensors to our model in order to train it actually. Now let's do the exact same thing for test set. So we want to create our test set. I just can copy and paste this train set to not waste time, and create another cell and just paste it here. And inside of the train, I want to change this to test this time. Torch Vision dataset, same thing. Instead of train equal to true, as I said, if we define it as false, so it will give us the test set. Download true, transform that to tensor. We don't change anything. So the only thing that we changed is the name of it. And then here we change the train equal to false. So it will download the test set for us. So if I run this right now, let me close this. And if I run it right now, you can see that file's already downloaded because we have downloaded it in this part and we extracted it. And I can even check out my test set. you can see that this is the CFAR data set, the CFAR 10 data sets. The number of data points this time is 10,000. So 10,000 for the test set, 50,000 for the training set here, and overall 60,000 data points and 60,000 images actually. The root location, same thing, and the split is actually set to test this time because train is equal to false. Okay, we have our training and test set. Super simple, right? Very straightforward, without any procedure for doing the train to split and these things. We have our train and test sets ready, and we have transformed it already to tensor as well. So it looks like something like this. And the next thing that we need to do is getting some information from this train or test set. So let's imagine that you don't have access to the link which gives you the related information of this data set. For example, saying that, okay, you have 10 classes and you don't know how many classes you have. In order to check that out, there is a way to do that. So first of all, I'm doing it like this. I'm saying labels is equal to brackets item 1 for item in train. So what we are doing actually in this line, we are saying that, okay, get all the labels in the train set, for example, in a train data set, and save it into labels, okay, as a list. So get all the items, item 1 for, why I'm saying item 1, because if you remember in a training set, we had the first tuple here that shows the specific image pixel intensity values, and the second item is actually showing us the label of the image, this one. So this is 0, this is 1. So we want this second item. So the position is actually 1. So I'm saying item 1, it means that this one, get this one for all the items in training set, for all the all of these data points in training set, and save them in labels. If I check the labels right now, if I check it, you can see that it takes time because it is getting actually all these 50,000 labels, for example. We have 50,000 labels, right? You have all of them here, but we don't want all of them. We just want to know how many unique labels we have here, how many classes we have. So the way to do that, instead of doing this, is using this set method. Okay, let's create a number of classes variable, and this is equal to length of. Okay, I'm using set method, and inside of this set I'm putting labels. So what does it mean? It means that use the set method and store the result in the length of these labels into number of classes. This set method is actually for finding the number of unique labels. So we define the labels, we have them here. To find the unique labels, we use the set method, and the length of it will actually give us the number of classes, how many classes we have. So if I run this right now, you can see that if I check the number of classes, then okay, let me add a print option here, so to print out what we want. So print number of classes. Let's put a colon also. Number of classes, and then just write the value of num classes. So if I run it again, it should print out the number of classes for us very perfectly. So we know the number of classes are 10, so now here it is also printed out the number of classes 10. So if you don't have access to the link of the data, and you want to check out how many classes do you have, you can simply use this method in order to get the unique values of the labels. Another thing that we want to check, and it is very important, let's create another cell, is checking out the shape of each image to give us some information about the image. Let's, for example, let's do it like this. Let's say image. Let's also get the label as well. Image and label is equal to, in a training set, for example, let's say we want to check out image number 20, right? And it will actually extract the image and label of train number 20 and save it for us. And we can simply print out, let's call it shape. And let's put a colon also. And then get the image shape. The same thing for labels. Let's put a backslash here and label. Oh, let's just call it label. And this is again colon, and the value of that is label itself. All right. So what we have done is getting the image and the label of that from the number 20 element, or let's say the image number 20 of the training set, and save it in image and label, and then we get the shape of that image and print it as shape and also the label of it. So if I run this right now, you can see that first of all the shape of this image number 20 is 3, 32, 32, and the label is 4. So what are these numbers? So first of all, in the shape, the first number is the number of channels of this image. For example, here is 3. And it means that our image is colorful image. So based on what we discussed in the previous tutorials, one channel when we have a black and white image, and 3 channels or RGB, red, green, blue, when we have color image. So the label is also set as 4, and the number of 32 and 32 shows the dimension of our image itself. So this is the channel, this is the dimension of our image, 32 by 32, and it refers to this image is related to label 4. It belongs to label 4 and class 4. That's based on here. Class 4 is 0, 1, 2, 3, 4. It should be the picture. So if I create another cell and let's check out what really look like this number, image number 20. Let's check that out. For example, I can use the imshow method in order to plot this. So I'm using the PLT method that I've already imported from Matplotlib, and I'm using the imshow method, imshow. And inside of the parentheses, I'm saying image, because this is the image, that's image of the image number 20. We saved it as image. I'm saying image.t. But why image.t? Before running this, let me explain this. So the reason for transposing, first of all, this t means transposing. So we are actually transposing the image. And why we are doing that? Because the inputs of imshow should be like this. Let me put it as comments. The input of imshow method should be like this, like m n like 3, for example. And what we have here is, what is it? Is 3mn. and M actually. So we have 3 and M. So this is the format that we have for the image, the shape of the image, 3 and M. But what we want is actually transpose of it for the imshow method. So that's why we actually need to transpose the image before giving it to imshow. So image.t is actually giving us that transpose. So that's transposing that we want. So it actually changing this to M and 3. And if I run this right now, it should give me something like this. It is somewhat clear that it's a deer, but let's actually make this a little bit more. The quality is not very good, so let's make this a little bit more high quality. So the default interpolation parameter in the imshow is set to neighbor. So what you need to do to make this a little bit better to read is using the bicubic parameter. So what I'm doing is actually setting the interpolation equal to bicubic. So if I run this right now, you can see that we have a better quality picture. All right. And it's somehow clear that we are talking about a deer. So we can also change this number. For example, change this instead of 20. Let's get the image of the image of, for example, 41. I don't know, some random numbers. And you can see that the label is 2. And the label 2, let's go back to the website. It refers to a car. Sorry, it refers to a bird, not a car. So it should give us a bird. So let's again run this. You can see that this time, I think it's an ostrich, I'm not sure, but it should be a bird. And for example, another random number, let's put 89, for example, I don't know. This time label 4. So label 4 is 0, 1, 2, 3, 4, again, deer. So let's make it to something not label 4. So let's put 57. I hope it should be something different. Again, 2. So let's make it something new. 48, for example. Come on, give us something new. Again, 40. Oh. So we are not... okay, now we have something else. So label 9. Label 9 is actually here, the last one, the truck. So it should give us the truck. Great. It's not clear that it is a truck, but it should be. So that's it. So we actually created, we actually checked we know how to check the image right now. And we also check the shape of the image and everything. So we understood actually we found out some very good information about our image dataset until now. The next step before the training step is actually creating batches. Let me explain this like this. So if we pass the entire dataset, about 50,000 images, imagine that. It could make the training process very slow, and it can even cause memory issues for us. And even larger data set, for example, this one is 50,000 images. Sometimes you are dealing with, for example, 1 million images or 500,000 images. So if you give the training set, the entire training set to your model in once, it actually, as I mentioned, it can cause memory issues, and the training process is also very slow. You have a computational time problem. Therefore, by dividing our data set into smaller batches, so we are not removing anything, we are just creating smaller batches from our whole training data, and we can make the training process faster and more efficient by giving those smaller batches instead of the whole batch, the whole data set in once. So let's do that. In order to create the batches, we can simply say train, let's call it train loader. Train loader is equal to torch we are using the Torch library, utils dot, I'm using the data loader. So to access the data loader, we need to call a couple of packages here, a couple of methods, and get to data loader. And then inside of the data loader, what we need to define is actually, if you just, it will give us some help to what should be defined. So the first thing is actually the data sets. Here, for example, is it our training sets. And you need to define the batch size, and if you want the shuffle it or not, and these things. So let's do that. Let's say our data set is train. We defined it before. And our batch size, I want it to be 100. So each batch contains actually 100 images. And let's put shuffle as true as well. Shuffle equal to true. All right. So we defined our train loader. So the next thing is do the exact same thing for the test sets, because we want to create a test loader as well. So just copy and paste this. Instead of train, just mention test loader. The exact same thing, just change this train to test, and let's put the batch size of the test set also 100. And let's run this, and that's it. We created our train loader and test loader that are ready to be used in our next steps. Now it's time to create our network. So in the previous tutorial, we actually read our data, we transformed it to tensor and also normalized it, and we also changed it to smaller batches, calling the data loader, and saved them in train loader and test loader. And now we have one step before training our training part, and that's creating the network actually that we want to train. So for creating the network, so we need to again use the class. Let's call it CNN, and our parent class nn.module, and colon. Now it's time to create our two main method. Just like before, it's init method and forward method. But in the init method, this time we need to define our different layers and our convolutional layers as well. So what I'm doing is, first, let's say define underscore init underscore self colon, and here I also want to mention I want to inherit the parent class to the child class. So I'm saying super empty parentheses dot init dot underscore init underscore, and again empty parentheses. Oops. Okay. And then I start to create my convolutional layer. So let's call it self.conv, for example. And this is equal to nn.sequential. And then I want to define this all these layers in this sequential. And what is this sequential? And then the sequential is a PyTorch container actually that allows us to stack multiple layers in a sequential order. So where the output of one layer becomes the input of the next layer. So that can help us very much. So we want to define actually our layers inside of this sequential container, let's say, inside of this container. So let's put enter, and let's define layer by layer here. So if you remember the first layer, first of all, if you have skipped the explanation part, I strongly suggest you to go to the explanation part, to the concepts, to understand them, and then come back to the coding part, because as I mentioned there, the coding is actually related to what we discussed in the explanation part. You need to understand these layers before we define them in Python. So if you have gone through that and you're familiar with these layers, that's fine. We can start defining these layers right now. So the first layer, if you remember, was convolutional layer. So the convolutional layer in PyTorch, we can just use this NN and call conv2D, this one, two-dimensional. So then inside of the parentheses, the first thing that you need to define, as you can see here as well in the suggestion part, you can see that you need to define the input channels. Okay, so the first thing is input channel. The second thing is the output channel. The third thing is the kernel size, and also the stride and padding and these things. So let's define all of these. So the first thing is the input channel. So I'm saying in channels is equal to 3. Why we will review these numbers together. Let's first define them. So input channel is 3, output channel, this one is 16, kernel size, this one is 3, comma, stride is equal to 1, and padding, let's put a padding equal to 1 as well. So what are these numbers? So the first parameter is actually the input channel. So the input channel, if you remember the CFAR10 images, they were colored image. So colored image, as we discussed before, they have 3 channels, RGB, red, green, blue, right? So the input channel is 3, that's why. And the output channel in here, we define it as 16. So why 16? This means that there will be 16 filters applied in the convolutional layer. So if you remember, in a convolutional layer, we discussed how we can apply the filter on our image. And then I explained that we can have as much filter as we want. For example, we can have 10 filters, we can have 30 filters. So it depends on us. So here, for example, I imagine that I have 16 filters. So this means that each of these filters producing an output feature. Okay, so this output channel will be the number of actually filters that you are applying on your convolutional layer and the number of produced feature maps. All right, so this is it. And the kernel size is actually the size of your filter or kernel. That is 3 by 3. If you remember, I told you most of the time we consider this as 3 by 3 matrices, but you can change this as well. The stride, if you remember, was the length that we went to the right by putting our kernel or filter on our image and doing it on and on, going across the image by this size. So this is the stride size, and this is the padding size. If you remember, for our padding, we just put 1 layer of zeros around our image. Again, if you are not familiar with these terms, you can go back to the explanation parts to review them. But the only important part here in this line is actually understanding these first two. The other ones are could be set. We discussed them before: padding, stride, and kernel size. This input channel is the number of inputs of our colored image, that is 3, and the output channel is actually the number of produced feature map based on number of filters that we define. We define it as 16. You can define it, for example, 32. It depends on you. And the next layer is the max pull layer. If you remember, after the output of the convolutional layer will be the inputs of the pooling layer. So for pooling, what I want to use is a max pull 2D. You can use other methods like min pull 2D, or as I said, there are a couple of methods for pooling, but the most famous one is max pooling. So let's use that. ns.maxpool 2D, this one. So inside of the max pool, the only thing that you need to define, if you remember in the pooling layer, we had a window size or kernel size or filter size that we put on the created feature map from the convolutional layer. And you need to define the size of that window. So let's say the kernel size is equal to 2. If you remember in the explanation part also, I mentioned that, for example, the kernel size is 2. So let's define that as 2 here as well. So the kernel size is 2. The other important thing was the stride in the max pooling. So if you remember, we had a stride length. So let's define that as well. Just like what we did in the explanation part, let's define this 2 as well. So stride is equal to 2, kernel size equal to 2, and that's it as well. Just do not forget to put comma after defining each layer. I forgot here, for example. So let's go to the next layer. So the next layer, if you remember, after convolutional layer and pooling layer, we need to pass our output through an activation function. What was that activation function? It was ReLU activation function. So we're saying nn.ReLU, ReLU like this, and then empty parentheses. That's it. We just passed it through an activation function. Then comma, and then we can define, if you remember, we can define as much as we want the number of layers, the convolutional layers and pooling layers in this ReLU layer. Let's define another layer of convolutional pooling and ReLU again. So let's define the exact thing like this. So I can just copy and paste this, for example, and then take care about the indentation is very important. And then just what I'm changing is, this is very important because the outputs of the max pool layer, this is actually the most critical part. The output of the max pool layer here in this layer will be the input of the next convolutional layer. So what was the output of the max pool layer? The output of the max pool layer will actually be 16 again. So if you remember the formula that we discussed before, right, let me just put a comment here so we can calculate one by one what's going on here. So first of all, let's calculate the outputs, the size of the output of our first convolutional layer. So if you remember, let me put a comment here. The formula was actually I minus f plus 2p divided by s plus 1, right? So this I was actually the input size of our image. This f is actually the size of the kernel, and p is the padding size, s is the stride length, and that's it. So we can easily calculate the output of the convolutional layer right now. So the only thing that we need to know is the input size of our image. So we haven't checked that before. So let's do that. So let's do this just like before, the creating code network. Let's create another cell here, and let's do it just like before that we have done this before, to check the size of our inputs tensors. So to do that, I can simply say image label. We have done this before, so you are familiar with this line. For example, train sets, get the first elements, no difference, and then print shape colon, go outside of this, and then image.shape. This is just like what we did before in order to get the size of the our input data. So let's put it like this, just like before. Let's say label, and then let's go outside of the quotation and put the value of it. So if I run this right now, it should give me the size of my tensor. So the size is actually, the label is 6, is not very important for us. This is important for us actually. So we wanted the size is 332 by 32. So this is the number of channels. So we use that number of channels here, 3. And then this is the size of our image, 32 by 32 pixel, okay? So if we want to actually calculate this number, so the I is actually 32. F is the size of the kernel, so it's 3. So let's do that actually. Let's say 32 minus 3 plus, what is the padding size? The padding size is 1, so 2 multiplied by 1, so it's 2 again. And let's divide this by 1, and then the final result plus 1. So 32 minus 3 is 29, plus 2 is 31. Let's divide it by 1 is 31 again, and plus 1 is 32 again. So you can see by adding this padding, if you remember, this was a rule of thumb. If you add one padding, the final feature map size will be actually the same size as your input image. So our input image was 32, and based on this formula, again, our output feature map will also be 32 in size. What about the, okay, so the 32 size feature map will be the input of the pooling layer. And the input of the pooling layer is this 32 by 32 size feature map. And the output of that, if you remember, there was a formula for there as well. So for this one as well. So we say M minus P, so let's put it as comment. So M minus P, and then divide this by stride lengths, and then plus 1 again. So M was the size of the input feature map, that was 32. So let's put this again here, 32. Minus P was actually the size of the window in our poolings, so kernel size is actually 2 again. And then divide this by the stride. For example, here the stride is 2. So let's divide it by 2 and plus 1. So, so as you can see here, 32 minus 2 will be 30, divided by 2 is 15, and plus 1, it will be equal to 16. So the output of the first pooling layer will be 16. So the input of the first convolution, second convolutional layer actually will be the output of this pooling layer, right? So the input of this should be 16. Simple, right? So the thing is, every time that you want to add second layer of convolution and pooling layer, you need to actually calculate this number and give it as the input of that layer. So the input of the convolution, this convolutional second convolutional layer, will be the output of this last pooling layer that we calculated it, and it was 16. So we put 16 here, and the output channel will also be the number of filters will be again applied of this input feature map. Okay, so let's say, for example, here this time we put 32 number of filters here. So the output will be again 32 number of feature maps actually. So we can simply copy the pooling layer as well and put it here. Let's take care of the indentation. Oops. Okay. And let's put the kernel size again 2 and the stride size equal to 2. And the last thing that we need to add is nn.relu. All right, that was it. And we can simply close this by this parenthesis. So the only calculation that you had was actually calculating what was the output of this pooling layer, the first pooling layer. So what will be the input of this convolutional layer? And that's it. That's the only calculation that you need to do in this sequential. So this was very important. So this actually was the only difference that we have between the convolutional neural network, CNN, from here to here actually. And a deep artificial neural network, for example. The rest is actually same as what we have done before for the artificial neural network as well. So the output of this conv layer that we created here actually will be the inputs of the fully connected layer, if you remember. So let's go to the next part and define our fully connected layer. So our fully connected layer, it should be just the same indentation with this self-conv. So we say self dot, let's call it FC, fully connected layer. And this will be equal to, again, I want to use this NN sequential. I like it very much because we can put all of our layer here as a container. So I'm saying again, NN dot sequential, and inside of the parentheses, I'm trying to define my layers. So the first layer is actually, okay, the first layer will be, let's put it as a linear layer, just like before. As I said, the only difference was this part. So this part is actually same as what we have done for the artificial neural network. So the inputs of the of this fully connected layer will be actually the outputs of our last max pooling layer. So here it comes. We need to do some calculations again. This is not a good news, but it is not taking so much time. So we need to skip this part, this calculation for the convolutional part, because I just gave you a rule of thumb that every time that you use a padding, so the input size of your convolutional layer will be the same as output size of your convolutional layer. So the feature map outside this convolutional layer will be the same as the input one. So the input here, if you remember, was 16. This is the input size, okay? So the output of this convolutional layer will be also 16 because I'm using the padding equal to 1. So you can feel free to just calculate this through this formula. It's free of charge. You can use it. And the inputs of this max pool layer will be 16. What will be the output? So the output will be actually, let's calculate this one. The output will be m minus p divided by s again plus 1. So what will be the output? So it will be 16 will be the input size of our feature map. Then minus, what is the kernel size? Again, 2. We use 2. And divide this by the stride length, that is 2 again, plus 1. So 16 minus 2 will be 14. Divided by 2 will be 7, plus 1, it will be 8. So the output of our pooling layer will be equal to 8, and that output of pooling layer passed through a ReLU activation function. It doesn't change any the size of that. And then the output of that ReLU function, that means 8 by 8 pooled feature map, it will be the inputs of this fully connected layer, that is NN dot linear. All right. So first of all, this should be same indentation of these ones. And here inside of the parentheses, I'm mentioning the input in underscore features is equal to, so this is very important. I'm saying 32 multiplied by 8 multiplied by 8. Why I'm saying 32? So if you remember, we use the 32 number of filters on the last layer of a convolution, and the outputs of this pooling layer will be actually 8 by 32 number of feature maps in the size of 8 by 8. So the input layer of the fully connected will be 32 multiplied by 8 multiplied by L. So this 32 is actually the number of filters that we use in the second convolutional layer. So the output will be 32 as well. So this will be the input of our linear fully connected layer, and the output will be actually the number of neurons, just like before. So we have 16 number of neurons, for example. Okay. So we put a comma here. Let's define another layer. So now we pass this through an activation function. So let's define a ReLU here. relu, empty parentheses, and do not forget to put comma, and then another, let's define another layer. Let's define, for example, let's say nn.linear, and define the input feature equal to 64. Let's define another layer with 64. So this is the input feature. That is the output of that layer. So because we have defined 64 neurons, the input feature of this layer, this hidden layer, will be 64. And then we can define another number of hidden layers here. Let's say, for example, output feature equal to 10 neurons. Okay, we don't want to make this neural network very huge neural network, so it takes so much time. When you're defining the parameters, hyperparameters, it is very important to be careful about the computational cost of this network as well. So let's put 10 neurons, just 10 neurons here, and that's it. That was our fully connected layer as well. So we defined our convolutional layers, we defined our fully connected layers. And if you remember, there was another method after defining the init method, and it was forward method, right? So we defined forward method, self and x, just like before. There's no need for sequential anymore. So you may ask, what about the flattening part? If you remember in the what we discussed in the explanation tutorials, one of the layers were actually flattening layer, that we passed our final output of the pooling layer to the flattening layer before feeding them to our neural network. And that's exactly what we are doing here in this forward method. So in the forward method, what I'm saying, I don't know why the indentation is not working properly. So in the forward layer, what I'm saying is x equal to self dot conv that we defined before, and I passed through this. So the first thing is I passed the x, I passed my data through conv self.conv that I defined here. This is the self.conv, okay? To pass them through convolutional layer, pooling layer, and also the activation function. Then this is the part that we are passing our final output of the pooling layer, this time to the flattening layer. So I'm saying x dot x. If you remember the flattening part, we have done this before, so you are familiar with that, x dot view. So I'm using the view method in order to flatten my input data, x dot size. And inside of this, I'm using this 0. And when I'm saying -1, it actually flatten my data. So I'm using this line in order to flatten the outputs of our self.conv here. The output of this will be passed through the view method in order to get a flattened data. And then the flattened data, the flattened tensor, let's say, will be passed through our fully connected layer. So let's say x is equal to self dot fc x, right? And then the last thing is return x. All right. So let's review it very quickly together. We first define our class and then define our init method. In the init method, we define our self.conv that's as a sequential that includes several layers, convolutional, the first convolutional layer, the first pooling layer, the first activation function, second convolutional layer, second pooling layer, and final activation function. Then we define our fully connected layer, including 2 hidden layers, one 64, second 10. And then we define our forward method in order to say that, okay, we want you to pass the x, pass our data through this conv layer that we created here, then pass it through flattening methods in order to make them flatten, and then pass it through the final fully connected neural net, fully connected layers. and then return X for us, right? So this is what we wanted for creating our network. And I think we have done it perfectly. Congratulations. The last thing that we want to define is actually saying that model is equal to CNN, this class that we created. We want to put all the information into a variable named model. And that was it. So let's run this. Okay, green check mark, everything is fine. So our neural network is created. The next step is actually creating our criterion and also the optimizer before starting training. So we do this just like before by saying a criterion. Let's call it criterion. I'm not good with criterion. I think it's fine. Is equal to nn dot cross. We use the cross entropy loss, just like what we did for artificial neural network, because we want to, we are using this actually the same data set in order to compare the result of the convolutional neural network with what we have done for the artificial neural network. So we want this comparison to be fair. That's why I'm actually using the same parameters here. I'm using the same metric for training part, for example, cross entropy. This is what we used for the deep artificial neural network as well. So the optimizer, also I want to use the same thing. Optimizer is equal to optim dot, I'm using the SGD optimizer, and model dot parameters, and the last thing is the learning rate that you need to define. Again, we select the same thing that we used for the artificial neural network to have a fair comparison, 0.01, and that's it. So these are our criterion and optimizer, and everything. If I run this, okay, I have a problem here. Method object is not iteratable, and that's simply because I forgot to put parentheses here. Run this again, everything is fine. So now everything is ready. Everything is ready to actually train this great network that we created. We developed our convolutional neural network, and now it's time to train this network with the input data that we have here, train loader. The process is 100% same as what we have done for artificial neural network. The only thing that I want to add here is the time. So we want to add import time, and also let's say start time is equal to time dot time. Okay, I'm calling the time from this time package that I imported, and also I want to print the output time as, let's print it like this. Let's say inside of the quotation, training took, okay, let's get the, for example, this time 2 decimal values and second. Okay. And then dot format, what is the value of that? The value of that is actually the subtraction of time dot time at the end minus the start time. Start underscore time that we define in the beginning, right? So this should actually print out the time that it took for our model to be trained at the end, and we can use that for the sake of comparison. So to define we can define the training part here in this bit in between these two lines, and what I'm doing is opening up the deep artificial neural network notebook that we have coded with together. So let's open that up. This was the neural network that we created with together, if you remember. in the previous tutorials. And this was the training part actually. So I want all the lines, because as I said, 100%, this is the same thing for the convolutional neural network as well. The training process is the same thing. So I just copy this, copy all these lines, Control C. So let's just get the whole lines again, Control C, and then go back to our convolutional neural network and paste this exactly here after this start time line, just like this. You can see that we have a couple of errors here, because first of all, the train loader in the artificial neural network code was train_loader, but here you can see that it's train loader. I defined it as train loader. So just remove the underscore here, here, and also here, and that should be fine. And we have a couple of other errors because of the indentation, I guess. So first of all, the indentation of this one should be below this for loop. So just put it below that one. You can see that it's gone. And also width, this width statement should be in the same indentation in this for loop as well. So let's correct the indentation, also correct the indentation of this one, and all of them. This one, this, and this. So this indentation is actually very important for us, because most of the time I also make this mistakes, and the student makes this mistakes, and they tell me that, okay, we have a problem, we just did as what you coded, but the problem is I get this error. And most of the time, 90% of the time, it's because of the indentation. So be careful about this indentation, and if you have any problem with the indentation itself, you can just copy and paste it from the original source of the code in your notebook and use that, or find out what is the exact problem in your code. Okay, I think everything is fine right now. So let's review what we have done. We added the timing, and printing out the time at the end, and in between we added the exact same process of what we have done for training of the artificial neural network. So we have done this, we should do the same thing here. Let's review it line by line. We don't go through the details, but let's review that quickly. So we created two empty lists in order to append the loss and accuracy during the training process into these lists, and then we have this is a for loop for our epochs. So first of all, let's change this from 50 to 30, because we don't want to have a risk of overfitting. And the 30, I think 30 is a good number. Let's start from lower number of epochs and then increase it if you want. So then we initialize the epoch loss. Then we got the images and labels from our train loader. We pass them through the model. We get the output, we calculate the loss, and for the backpropagation, we also calculate the loss and optimize it. Let's say minimize it actually. And then epoch loss, we calculate the epoch, we get the value of the loss, and we add it to epoch loss in every epoch. And then we added we calculated the loss with this epoch loss. And then appending it to this epoch list that we created here. And then we have gone through the same process for calculating the accuracy. Just I defined this in the with statement, and this with statement includes the correct and total values. I initialize that, and also a for loop just for getting the images again, passing them through the model, and also getting this line. If you remember, it was a little bit tricky, so I explained it like this: that the output data will be different different lists, including the value for each class. That we need to actually take the maximum value, but we don't want the value when we want the index, because the maximum value is selected as our predicted value. And we don't want the value itself, we want the index of that value that is selected. So we skip the value, we save the index of that value in the predicted variable. And then the total number of labels that we have, we got it from here, from the size of the train loader that we have. And also We get the correct values when we have the predicted value equal to labels. We sum them up, we get the value of that and save it into correct in each epoch. And then we calculate the accuracy based on the correct number of values that are calculated divided by total. And then we actually, at the end, we actually append this accuracy to the accuracy list that we created here. At the end, we print the output in each epoch, just like this. We want the accuracy and also loss to be shown in the progress of training. And that was it. That was the whole process. And everything is now ready actually our model is now ready to be trained. All right, so now everything ready to, we are ready to run this code. So let's run it. You can see that it will go through this for loop immediately in order to train our model, and it starts training. Then it goes to, for sure it goes to this part in order to calculate the accuracy and show it to us for each epoch. So it takes time. It takes about, I don't know, based on your computer, it may take about 10 minutes, 15 minutes, something like that, and based on the epoch number that you defined here. But the thing is, I need to fast forward this part in order to not waste time. And after the training part is finished, we will be back. All right, so the training part is finished now. You can see that we went through 30 number of epochs, and in 1324 seconds. This is the time, training time that is printed here. And just one important thing is make sure about the indentation. These indentations are very important. They could make several errors for you. So again, if you have any problem, just copy and paste this cell from the notebook that I provided in the source code, and you can simply use that and find out what was your problem if you have any error or something. So this training time could be different for you. It could be more than this, it could be less than this, again based on the configuration of your computer, so don't worry about that. And also the training accuracy and loss could be a little bit different for you too, but it should be somehow around this one if you went through the same process as I was. So as you can see, we have a training accuracy here around 70.73, that is about 73%. And our loss is about 0.6. What I want to do is quickly switch to our deep artificial neural network notebook again. So this was our artificial neural network notebook. This is the training process. We went through 15 number of epochs, and as you can see, the loss was 1.2. and the accuracy was about 57%. So even with less number of epochs for convolutional neural network, this one, even with 20 epoch number less, our accuracy is actually increased to 73% from what? From 57%. And also our loss is decreased to 0.6 from 1.2. So you can see that how creating a convolution layer here in our network, convolution layer, pooling layer, and all these layers that we used here are actually helping us in image classification, helping us to have better results with more accuracy, less loss, even with less number of epochs. So that was it. Just one quick things that I want to mention here is here in this section, in the RAM disk section, anytime that you want, for example, you're in the middle of this training part, you're in epoch number 15, and you understood that you don't want to continue this training and you want to change something and come back and something like that, you can stop that. And after that, if you run this again, it will start from what it was cut at. So the good thing, what it was cut. So the good thing is, go to this part, go to manage sessions, and then here you should terminate this. By terminating this, you actually terminate any amount of RAM that is used or any memory that is allocated to this notebook, and it will clear everything, and you can start from the beginning. But if you don't terminate this, you actually it start from where it was cut, and it will continue this. For example, from here, it will continue this again, the training. So the good thing is, and also the other thing that is good to know is you have limited amounts of data. So if you go to manage session, you have limited amount of RAM or memory, because we are using free version of the Colab, and it's not a premium version. So so the thing is, it is actually good every time that you are using you're running a cell, training your model in a notebook. After that, you terminate that and go to the next model, because you actually clear the used RAM, and you can simply use it for another model that you have, because you have limited amount, and if that limited reach, it will not work anymore. So that was it. In the next session, we want to test this model and to see how it works on the unforeseen data. It's time for testing our trained neural network. Before testing, I forgot to visualize the loss versus iterations. So it's a good thing to understand that if our model needs more epochs or not. So let's very quickly do that, and then we can start our testing part. So say again, x is equal to range 30, because we have 30 epoch, and we use the plt dot plot, and we want to plot x versus our loss list, and plt that's x label. Let's put the x label. Sorry, I put a extra underscore here. So let's put x as iteration, and also plt.y label. I put loss here. Then at the end, plt.show. So if I run this right now, it will give me the plots for loss versus iteration. As you can see, that still but by increasing the iteration, we are decreasing the loss. So we can actually increase the number of epochs. But the thing is, one thing, because we want to reduce the risk of overfitting as much as we can. So if we look at the last part of the accuracy, it's not clear in this image, but actually it is clear here, for example, from 29 to 30 and 28. So you can see we have a fluctuation here. Here it is, or even here, for example, from epoch 19, it decreased to 0.68 in epoch 20, and then it increase again, decrease again, increase until here that we have increase, and then we have decrease. So we have some fluctuation after epoch number 19, 20, something like that. So that fluctuation is actually not a good sign. So it means that if you have lots of fluctuation in your training accuracy, it means that you are increasing the risk of overfitting. So my suggestion is not increasing the number of epochs anymore. Epoch number 30, I think it's okay. Even you can reduce the number of epochs to 20 and check the results. And even with in 20 number of epochs, you will have same accuracy and loss, and also you will have you will reduce the computational cost as well. So let's keep it as it is, 30, and let's start our training part. Let me put our testing part. Sorry, let me put a note here that we want to start testing. So testing is also exactly like what we did for artificial neural network. So we just create a with statement. Say with dot torch.nograd, no underscore grad, this one. And then inside of this with a statement, I'm initializing the correct values to 0 and also the total values to 0 again. And then I define a for loop for images labels in test there's no underscore test loader. So oops, I forgot to put colon. And then the outputs will be equal to model images. We pass the images through the model, and then just like what we did for the training part, we get the predicted index values. So here we select the maximum value using torch max function, and we pass outputs dot data and 1. So this is exactly what we did in the training part as well. And we get the total in each iteration for test set. So labels dot size 0 and correct values. Again, in each iteration we add it to correct variable that we created when the predicted value is equal to labels value. All right, and then we get the sum. And oops, I forgot to add dot item here to get the scalar value of that. And then we print out. Let's print it outside of our for loop. So let's print. Let's say test accuracy. And then we get the only 4 decimal number, just like before, and we use dot format and puts the correct value to total number of labels that we have in a test set. So this is the exact process that we went through for the ANN as well. So if you have any problem, you can go back to that tutorial. We explain line by line this, line by line of this, and it's not very complicated. We just have a for loop here that's mentioning, okay, we get the image and label from the test loader this time, pass them through the model, and get the outputs, and also we got the predicted value using the torch max function. I explained this before how we can do this, and then we have the total number of labels, then we have the correct number of predicted labels when we compare them with the actual labels, and then if we sum this up and then divide this by total number of labels that we have, it will give us the prediction accuracy on the test set. So if I run this right now, it will start actually working on it, and it's quickly give us the test accuracy that is about 64%. So if we go back to our deep artificial neural network again, so this was the testing part, and you can see that the testing accuracy on the on-scene data was 52%. So we actually increased the accuracy about 12%, and that's not bad, about 13%. That's a good thing. That's a very significant amount of rise in the test accuracy. And even if we play around with the hyperparameters like learning rates, or like number of neurons, number of epochs, and number of filters that we are using in the convolutional layer, and all these hyperparameters, if we play around with them, maybe we can even get better results, something like 70% accuracy, something like that. And that's a good sign actually, that's showing us how convolutional neural network will be more powerful tool compared to the simple artificial neural network. So that was the testing part. And we can also calculate the, we can also create our confusion matrix based on this testing. So let's do that. I don't want to waste time, so I just go to artificial neural network notebook that we have. So here is the confusion matrix. So we can just copy and paste it from here. So it's the exact same process. We can just paste it in this cell. And the only thing that we need to change, as you can see here, test loader, we need to change it to test loader without underscore here. So this is the same process. We import the confusion matrix from scalar metrics, then a model.eval, then in a with torch no gradient statement, we actually go through the same process of testing. We pass the images through the model, we get the predicted value, we compare them with the actual value, and we create our confusion matrix with this for loop by putting the I and j in different as different elements of the matrix, I rows and j columns, and then the confusion matrix will be created, and we use this line in order to make the results as integer numbers in our matrix. And then we print the confusion matrix, and then this is the title of the matrix, and this is the print of the confusion matrix itself. So let's run this. It will take less than, I think, yeah, now it's converged, and now this is our confusion matrix. We can compare it with what we had before for the artificial neural network. And there's one thing else you can do. You can use this confusion matrix to calculate the accuracy that we have done here, the test accuracy. So you can extract the same test accuracy that we have here, 64%, from the confusion matrix as well. So what we can do is saying that accuracy is equal to, okay, the accuracy is actually these in diagonal of the confusion matrix, we have the correct predictions, right? These numbers. These are the diagonal of our matrix, and it will give us the correct predictions. And we can simply add them up by saying that, okay, confusion matrix, this one, just copy it and paste it here, dot the confusion matrix dot diagonal, this one, and empty parentheses. And sorry, then we want to sum them up. So we get the diagonal empty parentheses, that was right, and then we want to sum them up, and then divide this by the total number of predictions that we have, total number of labels that we have. So we need to sum all of these numbers up. So we say confusion matrix again, this one, confusion matrix dot sum. So we want to sum them up. At the end, we want to also multiply this by 100 to get the percentage of that. So we can print this out very simply by saying that, okay, F, I put this in quotation, accuracy, and then I'm saying accuracy colon dot to F in order to just get the two decimal numbers, and I put a percentage sign at the end to show it for us. So if I run this right now, it should actually sum up all these numbers in the diagonal of this matrix, and then get a summation of all these values. And then by dividing these two numbers together, it will give us the accuracy. Very simple. Run this, and it will give us 64.9%. Beautiful. So if we go up and compare this with the testing accuracy, you can see that 64.9%. We have the same thing here as well. Okay, so that was the testing part. We have done a very great job actually in this section.